Today's topic is unconstrained optimization problems, and today we are dealing with a multivariate nonlinear programming problem, and we will discuss some methods for solving unconstrained nonlinear programming problem which is having several variables. Now, whenever we are dealing with a multivariable several variable function, and if we just optimize the function, minimize or maximize the function, the efficiency of the optimization technique totally depends on the nature of the objective function. Now, if the objective function is convex in nature, then we will get the global optimal, but it is very difficult to check whether the function is convex or not, because for checking convexity we need to do the first order derivatives, second order derivatives of the objective function with respect to the variables concerned, and we will do some calculation for checking the convexity. Sometimes it happens that when the function is very much complex in nature, getting the first order derivative, second order derivative is also very difficult to obtain. That is why ensuring convexity is really difficult task for us. Not only that, if we see that the function which is involved in the optimization problem is not really continuous in nature within the given domain, then also if the discontinuities are there, then also it is very difficult to obtain the extremum, that is a minimum or maxima for the objective function. That is why in literature there are several methods for solving nonlinear optimization problems in general with some techniques, that is without going into detail about the derivatives of the function also we can just get the optimal solution using the searching technique. That is why in literature we can categorize the methodologies into two parts. One is the gradient method and another is the non-gradient method or direct search technique. This is one category, and another category is the gradient methods. Direct search methods are the non-gradient methods. We can list several methods in this one. The first method we can name it as a random search technique. Then we can go for the grid search technique, that is also very popular method for dealing with the unconstrained optimization problem. And there are several other methods also. One is the univariate method, simplex algorithm, that is another popular method for solving unconstrained optimization problem. This simplex method is different from the simplex method of linear programming problem, and in this category we can name another method that is also popular method, Hooks and Jeeves method. And in this direction another method is also there, that is Powell's method. These are all the non-gradient methods. As such, we will not really define the derivative of the functions, and we can still find out the optimal solution for the given objective function. But there are several gradient method as well for solving where it need some calculation for derivatives. One is that steepest descent method. Descent or ascent method, both are available depending on the minimization or maximization. And there is another method is also available, Newton's method. Quasi-Newton's method. These are all the methods we are using for solving unconstrained optimization problems. Today I will discuss some of the direct search method in specific for solving unconstrained optimization problem. Now let us start with the first, that is the random search technique. Rather in specific, let us go for the random jumping method. The method is very interesting method. This is totally dependent on the random numbers. We are having two, let us consider two variables, x1 and x2, and there is a function f of x1, x2, and we want to minimize or maximize the objective function, and there is a range for x1, there is a range for x2. What random jumping method does? It uses the random numbers. Nowadays, in the computer libraries, in the software, in the languages, we are having certain keywords for generating random numbers. That is why this method is very popular in the sense that we can generate random numbers, and if I just automate the process by writing a program, we can do it for solving unconstrained optimization problem. Let me discuss that method here. Now, what it does, say we are having a problem of several variable x1, x2, xn. We want to minimize this objective function. There are certain ranges for decision variables. The lower range is Li, and let us consider the upper range is Ui. We will use a set of random numbers. Before starting the method, we will generate n random numbers r1, r2, rn. After that, we will just do the searching technique. For searching technique, as we know, always we need to start the searching procedure from certain starting point, certain guess point. Now, let us consider the guess point is given to us. Now, what we will do? We will just go to the point x1. This is an iterative process. What is objective? Objective is to just update the approximate value of the optimal solution, so that we can reach to the real optimality after certain iteration. That is the objective. Now, we can generate the first point in this way, x1, x2, xn. How we can generate? We will use the n random numbers, and we will write it down as L1 as the L1 plus R1 into U1 minus L1. The second number L2 plus R2 into U2 minus L2, where L2 is the lower limit for x2 and U2 is the upper limit for x2. Similarly, I can go for xn as well, Ln plus Rn into Un minus Ln. With this, we will generate a number. After that, we will take another set of random numbers, say R1 prime, R2 prime to Rn prime. Again, we will go for x2. How we will go for x2? We will consider a set of numbers L1 plus Li, let me consider I here, Li, Ri, Ui minus Li, Ri prime. We will generate another number from here. In this, that is x2. These are all the points x1 and x2, these are all the points lying within the domain, because we have to consider random numbers in such a way that all random numbers will be in between 0 and 1. Then we will get a set of point within the domain. This is another point within the domain. In this way, generating another set of random numbers, we can generate another optimal point, and in that way we will have a list of objective functional value fx1, fx2, in the next fx3, and we can move further and further. After that, we will select the minimum one, and the corresponding xi can be declared as the optimal solution of the objective function. Now, what are the advantages of this method? That method advantage is that the method is very simple in calculation. We can automate the process by writing a simple logic with this, and this method works even for the discontinuous function, and we can capture the global extremum, that is the global maxima or minimum. Even we can capture the local maxima minima also, and this is the method, and that is very useful method. When other method fails, we are using this simple technique for solving unconstrained optimization problem. But one thing is that for better solution, we need to have several points together, and we need to have several functional values of the corresponding points as well. That is why if the number of calculations are more, we will get better result. That is the only limitation of this random jumping method. Now, let me discuss the next method, that is the grid search technique. That is another very popular method, and that also we can very easily automate. For example, let us have a function of two variables only, f of x1 and x2. We want to minimize this function. There is a range for x1 and x2. x1 lies between L1 and U1, and x2 let us consider in between L2 and U2. Now, this is the method, that is the grid search technique. This is x1, this side x2. What it does, we will consider the region, that is the L1 to, this is L1, this is U1, this is say L2, this is U2. Therefore, the function is defined in this region only. Now, we want to minimize the function, we will find out at which point function is having the minimum value, that is the objective of us. What the method does, it just partition the whole region into several grid points. These are the grid points we are considering. As many as we will consider, as many grid points we will consider, we will get the better result here. Now, after that what it does? We will just find out the functional value at each and every grid point, starting from here. At this point we will find out the functional value here also. In this way we will just move and we will just find out the functional value at each and every point, and from there, since the function is of minimization of the function, we will select the minimum value and we will just declare the corresponding xi as the optimal solution. What is the advantage is that this method works very fine for the lesser number of variables, but that is a very this is if we are having the problem with a large number of decision variables, then this method is not really good for that. But one thing is that this method is a good start for other method for locating the optimal solution within the range, and that also very easy to calculate. Here also the same thing, the advantages are there, just like the random jumping method, that this method works even for the discontinuous function, and not only that, we can have the global minima or global maxima for the function with this method as well. And these are very simple technique for solving unconstrained optimization problem. But one thing is that we will say that method is the best method where we need to, the method should have the lesser complexity, and not only that, we need to do lesser number of computations. That is why afterwards several other methods have come out to solve unconstrained optimization problem. One popular method is the simplex method. Let me discuss simplex method for solving unconstrained optimization in the next. simplex method, this method for solving nonlinear programming problem it is different from the linear programming problem, but the concept of simplex is same here, where we have to consider in the simplex method the convex hull with n plus 1 number of points in n dimensional space. Now, as such, if we consider a single dimension, then a line segment would be a simplex. If we consider the 2 dimension, a triangle would be the simplex. If we just consider the 3 dimension, a tetrahedron, in that way we can extend further and further, and we will get the convex hull with n plus 1 number of points in n dimensional space. That is the simplex. Now, if we are having all the points are equidistant, that is the sides of the simplex graph, if these are all same, then we will declare that simplex as the regular simplex. The whole simplex method is based on this simplex technique, simplex concept. Actually, what we will do from the n, we are considering a function in n dimensional space, because there are n number of decision variables. We will consider a simplex of in the n dimensional space. We will start with a simplex, and we will update the simplex in such a way in the respective iterations further in simplex method, so that we can reach to the optimal solution as quickly as possible. That is the philosophy of simplex method. That is why we will first task is to develop the simplex, next to just show the method how the simplex will be updated to get the better result. Better in the sense we are considering the objective function, that is the minimization of f of x1, x2 up to xn, where n number of decision variables are involved. Now, let us consider a simplex initially. Let the simplex be this one with these points only. As I said, if we consider here x1, x2, xn, this is in the nth dimension. Now, a simplex we need to consider with n plus 1 points only. That is why let us take the points x1, x2, x3 up to xn plus 1. This is the, let us consider initial simplex with these points. Now, for starting simplex method, we need to define certain things. First of all, we need to find out the functional values at each and every points, at the corner points of the simplex, fx2, fx3, fxn plus 1. These are all the functional values at simplex point. Now, after this, we will find out few values. We will consider, since we are looking for the minimum value of the objective function, that is why within this set where n plus 1 number of functional values are there, we will prefer the minimum value. That minimum may not be the optimal solution, but still, since we are starting the process with this set of values, we will prefer the minimum value and we will discard the maximum value. That is why we are selecting 2 points, one is the best point and another one is the worst point. The best point is that, let me call xh, this is equal to maximum of all fxj's, where j is running between 1 to n. This is the worst alternative for me, since the problem is of minimization. If we do the maximization problem, this is the best selection for us. And we will select the best alternative within this set by considering the minimum of all these functional value. How it looks like, how the simplex looks like. If I consider in R2 dimension, that is a 2 dimensional space, I can consider this is x1, this is x2, this is x3, and that would be the simplex in 2 dimension. What the simplex method does, in the next stage where we are having the high functional value, we will just discard that functional value and we will move to the next value x4, so that say x1 is having the higher value, then we will construct another simplex in the next. This is my next simplex. What is the objective? Objective is to get the better minimum value. That is why x4 must have the better minimum than x1. In that way, again we will move to the next simplex. In this way, we will proceed further and further. In this way, once we are proceeding, there is a guideline, there is a process for movement, and the whole process is dependent on few operations. First operation is the reflection operation. Second is that contraction. And another operation is the expansion operation. And these the methods depending on certain parameters as well, that is called the reflection coefficient, and we are just naming with alpha, that is my reflection coefficient. And we are considering gamma as the expansion coefficient, and beta as contraction coefficient. And there are certain specific values for this alpha, beta, gamma as well. There are certain conditions for it. Always alpha is greater than 0, beta in between 0 and 1, we can prove it also, and gamma is greater than 1 and gamma is greater than alpha. How the whole process is dependent on these parameters alpha, beta, gamma, I will just show you in the next. Now, here one thing should be mentioned once we are starting with the initial simplex. Now, initial simplex is we can have the regular simplex as well if we want, because regular simplex means the sides of the simplex are same, that is the all the points are equidistant. For generation of this also there is a guideline. Before going to the simplex detail, let me just tell you first how to generate regular simplex. This can be considered in the initial stage only, because afterwards the process will guide us to the next simplex automatically. Now, how we will start from an initial point x naught. X naught means we will consider small x naught, because in the simplex there will have n plus 1 number of points. We will start from x naught and we will move to the next x1 with this logic. Let me consider xi, where I will run from 1 to n. Xi would be is equal to x0 plus p into ey plus j is equal to 1 to n, I naught is equal to j uj, and considering I is equal to 1 to n, then only we will get n plus 1 number of points in the simplex, because we are having x1 and we will generate another n points. And if we want the side of the simplex of length a, then the parameter value p, and here it is a q. The parameter value p will be is equal to a by n root 2 root n plus 1 plus n minus 1, and q would be is equal to, if we consider in this way, we will just apply the value for a and n, and we will get the value for p and q, and here ui, ej's are the unit vectors we will consider in the respective directions, and we can have the regular simplex. The respective direction means we will consider the unit vectors in the coordinate axis direction. We are considering n dimensional space. In that way we will consider the, in that way we can generate the regular simplex. This is one part for solving, for generating the initial simplex, but let me start the algorithm for the simplex method in the next. What we will do? We will calculate the centroid value. The centroid will be calculated with x bar equal to 1 by n summation x j's. J will run between 1 to n plus 1 except one point where j is not equal to h. That means we want to reject the point which is having the highest value, objective functional value. That is why we are considering j not equal to h, and we will select all other n number of points and we will divide with n and we will get the centroid. For example, if we consider a triangle, if this is the triangle for us, x1, x2, x3, if x1 gives the higher value of the objective function, then we will get the centroid, we will calculate centroid with 2 points x2 and x3, and that will be declared as the centroid value x bar. We will just we will not consider the point x1 here. This is the starting point. Next, the step 1 starts. We need to calculate, actually next the reflection process starts. How to do the reflection process? We will calculate xr is equal to x bar plus reflection parameter into x bar minus x h. Now here alpha has been considered as greater than 0. If this is so, x bar is the centroid value without x h. That means we are generating another point xr. How, where it will be? If I just do it here graphically, then here xh would be is equal to x1 as we have considered, then we will generate another point here as xr. That is the through the reflection process we are getting this one. After that, in the next we will see what is the functional value in xr. If we see in xr the functional value is higher than x1, then certainly this is not preferable to us. But if we see xr is having the lesser value than x1, then in the next case we will reject x1 and we will consider the next simplex as x2, x3, xr. Okay? That is why we will rename it with x1 now. Now that process I am doing in the next. That is my step 2. After reflection, if f x L is greater than f x r, that means f x r gives better value than the lower value even. That is why f x r must be preferable to us. And What we will do? We will, if this is so, we will replace x higher with xr. That means in the next simplex we are rejecting xh and we will select xr as another point, and we will move to the next step, step 2 for expansion process. But if it is the reverse case, that means if we are having fxr is greater than fxl, then in that case we will move to, that is step 3 for expansion, and we will move to step 4 for contraction. That process now I am going to just elaborate in the next. Step 3, that means if we consider after the process, if we see that reflection process, if we see that fxl is greater than fxr, then we have to do the expansion process with the expansion coefficient. And what is the meaning of it? It means that we can see here, it means that if I just move in this direction, how we have generated xr, that is in the direction of x bar minus xh, in this direction. And the thing is that if I just move in this direction further, there is a possibility for better objective functional value. That means we will get the minimum lesser value of objective function in this direction only. In the expansion process, we will do the same thing here. What we will do? We will generate another point x e. How x v would be is equal to x bar plus gamma into x r minus x bar, where gamma is greater than 1. If I just see the figure here, we will see that if this is the initial figure, x1 is having the higher value, what is alternative for us? We will not care for the best alternative because we want further improvement of the objective functional value. We have x bar here and we are getting xr, and we are moving in this direction only with this expression x bar plus gamma into xr minus x bar, where gamma is greater than 1. That is why we will move to another point in this direction only to xc. Why we have done so? We have moved in this direction because we are expecting that we will get better minimum value. That is the reason for us, but we have to check that value, functional value as well. And once this has been done, we will reject the previous simplex and we will update the simplex. Just how, I will just show you in the next. After that, we will calculate the functional value at xc, at the expansion point. If we see this is lesser than L, then replace xh, the higher value always will be replaced with the better one, and go to step 2 for further reflection process. Because we want another improvement, again we will go for reflection, again we will expand it and we will go to the better and better alternative. But if the case is otherwise, then we will move to the next stage. That means we will say that the expansion process fails. In that case, we have to do the reflection process once again. But if in the previous case, if I go to the previous step, we have considered that if XL is less than greater than FXR, go to the expansion, otherwise go to the step 4. That is why in the step 4 our condition is that FXL is lesser than FXR. That means FXR is having the value lesser than FXL, but it may have the value FXR can be greater than FXH, or it could be can be lesser than FXH even, because we are doing the contraction process. This process is the expansion process. With the example we can see it very nicely. Now, we are doing now, if this happens, in that case we will find out the minimum value of find out X star in such a way that where Fx star is minimum of Fxr and Fxh. What it will be done in the next, just if I just write down the simplex once again, we have done the reflection process x2, x3. This is the x bar, we have done the reflection here. In the contraction process, what it does, in the contraction process we will not expand it, we will not go further, because we could see that if I just move up to XR, the functional value we are not getting better one. That is why we will just move to the left side in this side, and we can generate this point and we can generate here also. That must be within the within this region. That is the process of contraction. That is why this process is being named as the contraction process. What is the objective? Objective is to just move around the whole space and looking at the pattern of the objective functional value, we are trying to guess in which direction function is having better minimum, and we will move in through that direction only, because since we are considering the multi-objective case, there are infinite directions we can move from one point to the other point. That is why we have to move to the next point in such a way that always the functional value will be better one. That direction we want to find it out, we want to just analyze, we want to guess, that is the thing. Now, we will find out in the contraction process, that is my xc. We will find out the xc in such a way that it will depend on the contraction parameter in this way, x bar plus beta into x prime minus x bar. And as we know, the beta value is always in between 0 and 1. That is why looking at the expression, it is clear that we are considering x bar minus something. That is why we will just we will x bar minus x prime minus x bar. Instead of going to further, we will just move to the in this direction. Now, here just I want to mention that if x bar is equal to xh, that means if xh is lesser than fxr, then this xc would be like this, xc would be is equal to x bar plus beta into xh minus x bar. All right. This is my xh, this is my x bar. That is why we will just move to the reverse point. That means if this is the simplex, initial simplex, this is xh, rather x1, x2, x3. After reflection we have reached to xr. this is my x bar, then beta is in between 0 to 1, that is why we will just move to this point, certainly in this direction. Alright, this would be my xc, and this would be the case. In this case, we will have x bar is equal to xr. That means f xr is lesser than fxh. Alright. We will repeat the process again and again to get the functional value. The whole process can be just see in a with an example. Just see, let us, we are having in 2 dimension. We can have the function in this way. These are all the functional contours, at minimum lies here, say. Alright. We are doing our operation. We can start the initial simplex with this 1, x1, x2, x3. Since the function is a minimization function, this side x1, this x1 means objective functional value x1, and let me not consider this as x1. Let me consider this as just number 1, number 2 and number 3. Now, if this is so, then it must be clear that at point 3 the functional value is having higher value. That is why the next simplex must be rejected. In the next simplex 3 point must be rejected. That is why we will do the operation. Since it is having the higher value, we will get the middle value of this, that is the centroid value of 2 points, and we will just move with this direction and we will move to the next value. That would be the number 4 for me. And since functional value at this point at numbered 4 point, functional value is better one, is having the lesser functional value. These are all the function contours. That is why this point is again acceptable to me, and we will just move, we are moving to, we will reject 3 and we will consider in the next iteration we will consider this simplex. Now, this point is having higher value than these two, that is why we will consider the centroid here and we will move the reflection, we will do the reflection process in this way and we will move to 5th point here. Again, if I just see the points, f5 is having better value than x1, that is why in the next we will reject the simplex, we will reject the value phi 1. In the next simplex we will consider this simplex again. And if I just see the path, how we are moving from this point and from here to here, if I just see, then here, that means in a zigzag process we are moving. Let us see what is happening in the next. This is having higher value, these are having lower value, that is we will move to the next in this way, alright. And after that, this we will reject this point, this is 6, we will move to the next. In this way we will proceed further and further and go to 7, and ultimately we will reach, our target is to reach to the optimal point. This here is the optimal x star for us. And in the process, whenever required, we will do the expansion and we will do the contraction. That is the whole idea of the simplex method. And let us apply the simplex method for some example. But one thing should be mentioned here, sometimes it happens that we will just fall in the expansion process, in the reflection process, we will just proceed in such a way that we will just fall automatically in a cyclic loop. We have to update the process in such a way that we should not fall in the cyclic loop. The one consideration is that one restriction we can make in that way. In the process, if I just move instead, I can show you one example for this. If this is the example. Now, this example has been considered, just see here x1 is from the, this is x1, this is x2, this is x3. x2 is having higher value than x1 and x3 certainly. That is why x2 is rejected. After that we are doing the reflection process, we are moving here. Where we are moving? We are moving somewhere which is having the lesser acceptance, that means is having higher functional value. That is why if I just move in this way, it may happen that we will be far from the optimal solution. That is not accepted really for us. That is why we should not move in such a way that we will fall either in a reverse direction or we will just fall in a infinite loop. That is why the contraction and the expansion process is there to control our movement. That is the idea altogether. Let me just do some example with it. This example I have considered from a book, that is Engineering Optimization Theory and Practice by S.S. Rao. That is very popular book in optimization. I am considering this one example from here only. The problem is that we are having two variable objective function, minimize fx1 fx2 is equal to x1 minus x2 plus 2x1 square plus 2x1 x2 plus x2 square, and it has been given that take the initial simplex since this is of R2. That is why in the initial simplex we will have 3 points that has been given here 4.0, 4.0, x2 is 5.0, 4.0 and x3 is having 4 and 5. What else has been given? It has been given that the reflection parameter value is 1, since alpha value is given here 0.5 and gamma is 2.0. Now, it has been also mentioned that for convergence use the stopping criteria as epsilon is equal to 0.2. One thing should be mentioned that since this is the process of iteration, we are doing reflection, expansion and contraction in a series in a sequential manner. Whenever required, which operation is required, we have to implement that one, but we have to stop somewhere. There is a guideline for stopping the process is that either we have to stop in that point where since I am having a list of functional value at each and every point, we will consider that is the last simplex with n plus 1 number of points, and after that we will just find out the standard deviation of all functional value at that simplex. That means we will have n plus 1 functional values. If we see the standard deviation is very small, then we can stop our process. This is one idea for processing, for stopping the iteration. That is why it has been mentioned that for the convergence consider epsilon is equal to 0.2. That means we will consider that the standard deviation of the functional value at the last simplex must be less than 0.2. And another criteria also we can adopt if it has been specified before that we have to do this number of iterations. That means we have to generate this number of simplex. Then there also we can stop our that totally depends on the experience, and otherwise we have to repeat the process again and again. This is the whole thing for us. We will just start our process. Now, we will first find out the functional value at x1. We will see the functional value will be 80. we will go for the functional value f2 as 107 and f3 the functional value at the point x3 f3 it would be 96. If we just see the functional values from here, it is very clear. This is the worst alternative and this is the best alternative. That is why in the next we will select xh, the highest one as x2 and the xl would be my x1. Now we will start our process, we will go for reflection. What is the reflection process? We will generate the centroid value x bar. How we will generate? There are 3 points. We will just discard x2, that is why we will consider the mid of x1 and x3. If we consider mid of x1 and x3, we will get the value will be 4 and 4.5. We will see the functional value at centroid. This centroid value is coming 87.75. Now our process, reflection process will start. How the reflection process will be done? We will generate XR. How? X bar plus alpha into x bar minus xh. Here my x bar is 4.5, xh is x2, that is 5, 4. In this way, if I just do, we are getting this is x bar 4.5 plus alpha we have considered is equal to 1 and here we are having, that means if alpha is 1 we are having 2 into x bar minus xh, that is why x2, that is 5 and 4. Oh, this 2 is there, 5 and 4 and we can get the value as 3, 5. We will see the functional value at XR. The functional value is coming 71. Now our process starts, whether we will go for expansion or not we will see. What we see that my lowest value fxl, that is the lowest point was my x1 point, that the functional value was 80 and we are having now 70. That means we are getting fxr lesser than fxl. Then what is the thing? We need to do expansion, because I know if I just move in the direction of x, in the direction of x3 x bar, I will get better minimum. That is why we are doing the expansion in the next. How to do expansion? As we know, the xe we will just generate x bar plus expansion beta into x reflection minus x bar. What is x bar here? 3 and 5, beta is equal to 2, that is why we are getting 2 into xr, that is 2 into 3, 5 minus x bar is having 4, 4.5. That is why we are getting the expansion value as 2, 5.5. What we get again at point xc, the functional value is coming 56.75. That means we are getting better minima. That is why we will repeat the process further and further in the next step. Since fxc is lesser than this, that is why again we will replace, we will have the, just if I just write down the simplex in this way, we could see that x1 is having the higher value, lower, no, it is the lower value, x2 is having the higher value, x1, x2. We are moving to the x bar, then we are going to reflection xr, then we are moving further and we are going to xc in this direction only. Since we are getting better minima, we will extend, we will again apply the expansion process with the new simplex. Then what is my new simplex here? My new simplex would be x1, x2. Since we are doing the expansion process, that is why we are having the value xc and we could see that we are getting the better minimum value at this point. That is why if I just go back to the simplex figure, x2 was the worst alternative for us. Now we are getting another better alternative xc. That is why I can consider the new simplex as x1, x2 and x3, where x2 will be xc is becoming x2 now. That is why in the new simplex we will have x1 that was 4, 4, xc is my new one 2, 5.5 and x3 will be the previous x3. Now, this is my new simplex. I do not know whether I have to stop the process or not. For that thing we need to find out the standard deviation of the functional values. Since we are having fx1 say f1, fx2 f2 and fx3 f3, then the functional value can be, the standard deviation can be find out in this way, that we will find out the mean of these three and we will find out the formula in this way, 1 by n summation fxi's minus mean of these functional values square. I is running from 1 to n plus 1, it should be n plus 1, 1 by n plus 1 into I is equal to 1 to n plus 1 fxi minus fx bar whole square. If I just do it for this one, we are having all the functional values with us, we can calculate like this, the 1 by 3 and here it will be first functional value fx1 was 80 and mid of all functional values f1, f2, f3 is we can get it 87.75 this square plus x2 functional value is 56.75 minus 87.75 whole square plus functional value at x3 just now we got as 96, that is why 96 minus mean of all these functional values square, and this value is coming as 19.06. This is not less than epsilon, epsilon has been provided as 0.2, that is why we need to do the next. How to do? We will repeat the process starting from reflection with the simplex this one. In this way we will proceed further and further unless and until the standard deviation of the functional value is reached to a smaller value, and at the end we will declare that the last simplex, whatever simplex we will get from there, we will select the optimal solution. Now, that is all about the direct search method, and we will get the centroid of the final simplex as the optimal solution, and that is all about the direct search method, we can, this is non-gradient method because we did not use anywhere the derivative concept, and in the next for better result for if the function is continuous we can move to the gradient method where the whole process will depend on the differential coefficients. That is all for today. Thank you.